I'm gonna need a few of these. All right. Let's see. All right, so we got, see what we got this paper. It looks, yeah, it's pretty imposing.
Just 6 pages.
Well, it's a letter, a macro letter. It's short can be bad. Don't get excited about short. So, and also they have supporting info. That's part of it. So they keep referring to S1, S2, S3. So it can be 6 pages because the supporting info is only 11 pages. So actually it's 17 pages when you add it together. So the letter format is kind of a funny thing. People have morphed it into. Anyway, so this is about this Ken Schweitzer. So there are 2 guys, Kuro and Schweitzer. In the 1990s, they came up with a thing called Prism, a computer program or computer algorithm, I guess, to look at to get the structure factor for polymers and melts, right? So anyway, this is a pretty nice, this guy, Tyler Martin, he's at NIST. So he wrote a pretty nice, this has Ron Jones is the NIST guy. Gardner name is familiar. I don't remember who he is. He's not at NIST. And then Arthi J. Raman is a simulation person at Delaware, like kind of one of the rock star young simulation people. Does some Prism stuff, but not that much. The main thing is Schweitzer, because Kuro retired. Where are these other guys? Summary, correspondence. Sometimes it says where they're from, right? To the end. I don't know why they don't just put it at the top. Anyway, somewhere it says where they're from. I don't know where the other people are from. Acknowledgements, summary. So where's their home address here?
You see that?
Oh, right here. It is at the top. This is an old, because 2018. And maybe they've changed to put it at the top. So they're both at Delaware, I guess. All the double symbol ones are at Delaware. Gardner, I don't know him, but I think anyway, he sounds pretty familiar. Someone I should know. And Jones and Snyder's at. Anyway, so they go through. This is a pretty nice thing, what they do here, what Tyler does. He goes through like all what you call the free and open source software, just like stuff, because someone said like this density functional theory, that the program is going to cost like so much money that you can't afford it if you're in Africa, if you're in South Africa. So basically, they can't use any of the stuff. So these are things that you can use because they're free and open, like lamps, like we've talked about lamps already. And Nichols talked about Gromax for protein things. And then there's a bunch of them here. Hamid Blue, there's also like lamps. So these are molecular dynamics things. But I guess for density functional, there's a bunch. Like, so density functional is going to be like electron density of atoms, right? To get like conductive state or something. So some metallurgy thing mostly. But right, there are some like espresso. There are some free programs that you can use for that stuff too. Generally, like in polymers, you don't do density functional theory. It's more for semiconductors and things. Maybe if you're doing like conductive polymers, something like that, you might use it, So it's like for electronic properties based on atomic level things. And then lamps, these are going to be for mesoscale, like molecular dynamics goes up to like maybe sub-micron, like nanoscale things. atomic to nanoscale, and then self-consistent field theory. I don't know much about. There's only one he lists. I want to look that one up. And then finite element is mechanical engineering. That's like you're going to break your thing into a grid, and you're going to look at the mechanics of if you bend it or something. Right. So finite elements for really large scale, like millimeters, maybe up to meters, or they can do bridges with finite element or buildings and things. Right. So anyway, these are all free programs. So it's nice he lists all of them, all the ones that current in 2018. And then probably the first ones like are the most popular, like Espresso, lamps. So those would be the first ones he lists are probably the ones that you would use, and the others you probably wouldn't look at. Because if you look at lamps, if you Google lamps, so you could Google lamps in any question that you could possibly have, and you'll find out someone's already written code in it, and you can just copy what they did. And it's a open source. That means they can add in parts to the program. So whatever, if anyone does one thing, and it makes a program like expand, like a web, so basically lamps, you can do anything in it, and it's already been done mostly. So you might just have to tweak a little bit what someone else did, and then it makes it a lot easier. Homemade Blue is kind of faster or something. It can run better on video cards or something like that. So it's better than lamps, but basically it doesn't have that network of users. So really the power of these things is the network of users. So you're taking advantage of things that are already done. So whether it's slow or fast doesn't matter as much, because the computers keep doubling the speed. So even if it's a slow software, it's already double the speed just if you wait a couple of years. So I mean, and you can do these on a PC now. If you buy the graphics cards, so they'll run on the same cards you use to run the computer games. Anyway, and those are like high speed, single purpose kind of functional things. So, or you can get like Ohio supercomputer, you can get $5,000 worth of free time. So if you want to use lamps, all these programs are already loaded onto Ohio supercomputers. So you write whatever you want to do, the algorithm, which would be a script, and then it's going to repeat that script over and over again to do whatever simulation, move the molecules, there's a force field, there's a spring or something, right? Do that over and over for 1 billion of these things. So basically the script can be relatively short. Because you're doing the same thing for all these things. You just want to see like how it emerges out of that, what comes out of that thing. So anyway, so you can do that. You can get the free thing going on your PC and then mess around with it, get it set up, and you can go to Ohio Supercomputer. And $5,000 will give you a lot of, that's basically like a year work they give you for free. So so there's no excuse not to do this if you have any inclination to do it at all. Yeah. Or you can just go borrow someone's lab video card system, because there's a lot of them around, and basically they only use them like for a week in the year, and then there's the rest of the year left where you could just borrow someone's. So there's plenty of computer power, and even if you use like a laptop with all the chips on them now, especially if you get a desktop computer and you put video cards into it, so like maybe $500 or $1,000 per video card, you can get like 10 of them, and then just that's what these desktop units are. So just loaded with video cards, and then however many slots you have in the motherboard. That's kind of what decides it. Anyway, he goes through kind of what's going on here. So he says, so this paper is about PRISM because it's from Schweitzer, so Schweitzer and Kuro were at Sandia, and they developed this PRISM algorithm like in 1992 or something like that, in the 90s. Then they pushed this thing, and it became like Rockstar for a while, like a Rockstar program thing, and it could solve anything. And everybody picked up on it to try to calculate correlation functions. And then they pushed it to talk about calculating the interaction parameter and things. So it's based on this, the Ornstein-Zernike we talked about. Like you want to know the correlation function, say in a mixture of things. So the Ornstein-Zernike function, and again, like Zernike won the Nobel Prize, but not for this. He won it for the confocal microscope. Ornstein didn't win it, although this is the basis of like a huge chunk of what people are doing. It's how you figure out how the organization of things happen, atoms in particular, molecules. Like so So basically the correlation function for the mixture is made up of, if you had just a binary, like two things interacting, and then what happens if you put in a third thing, and then how that would impact the two things, right? So you have the binary correlations. If they were in dilute solution, two things happen to interact. And then when you put in other things, that impacts all three, right? So you have the problem that interactions, it's a recursive equation, and that the interaction of 1, 2, in other words, when you get 3, it's going to be the interaction of 1, 2 times, it's going to integrate all the possible interactions of 1, 2 between the three, like 1, 2, 1, 3, and then and all the possible combinations of those, right? So you can't solve it because you're defining the thing in terms of itself. So you need a closure relationship to solve that. So the closure relationships we talked about are like cyclic, or in groups are free, or something like that, right? So you have some kind of equation that you need one more equation to solve that equation. So that's called the closure relationship. So that's liquid state theory. So that was what do they give a date on this? I think that was early 1900s, something 1920 or something. Ornstein's very kid. 2021. So when's the original one though? There's no dates on these things. It's like early 1900s, 1914 probably. That's probably it. So anyway, so then in 1972, this guy Chandler came along, right? So who was at Berkeley then? So he was at Illinois. So any things are named after him, I guess. This is the guy. I think he's dead now. 2017. So like 72, he came up with the idea, like, so that was basically binary or single molecule interactions of the Ornstein-Zernike. They said, like, what if you have like ethylene, like a short organic molecules in solution? Then want to get the correlation function of that. Well, it's going to involve like this integral becomes much more complicated, because you have to have the internal interactions and then the external, so inter and intra interactions within the molecule and outside the molecule. And then so he adds in another integral, and then you need computers to calculate it. So he developed this rhythm theory, which stands for something, I don't know what it stands for. There's a bunch of rhythms. Rhythm theory, they call it rhythm. Reference interaction site model. So it basically is integrating over all the possible interactions between a system and in a bulk system, you know, so it's a lot of integrals you have to do. So that almost got him the Nobel Prize, like doing that, because everybody copied it and used it, but he didn't get it. But basically he could have, he was like a shortlister of it. So then, so 20 years later, these jokers show up at Sandia in the middle of the desert, New Mexico, and like come up at a nuclear bomb factory and come up with this, and they have a lot of computers, supercomputers, like coming out of their ears. So they want to do the Chandler thing. So the problem with the Chandler thing is if you try to do it for high molecular weight polymers, and Tyler discusses this in his thing here, pi prism. So he goes through, like, it doesn't work. Like Chandler's thing doesn't work if you try to do polymers, because it's too complicated. Because the integral goes on forever, the computer blows up, right? So Kerr and Schweitzer figured out a way to minimize that problem, and he kind of discusses in here. I think he knows more than I do about it, but basically he discusses how that can work out, and what it spits out is a correlation function for a polymer melt. And it can, from the correlation function, you can get things like the structure factor from scattering, in other words, the scattering intensity. You can get the chi parameter for a blend of things. So you can get a bunch of things from it that are kind of useful if you want. And then, so basically he's using that with nanoparticles here. So Schweitzer's the guy that invented prism, and he's using it to talk about nanoparticles. Okay, so that's the theme of this paper. So it does have like a lot of baggage with it. In other words, it isn't just this paper. So it's kind of interesting. And then I think Sue is just a grad student at the University of Illinois. So it's funny, like so Chandler was like MIT, Harvard, and then he went someplace, and then he went to Illinois. So he was at Illinois for a while, the guy that invented RISM. And then he went to Berkeley and kind of became associated with Berkeley. Like if he had won the Nobel Prize, it would have been at Berkeley. And then these guys, Schweitzer was at Sandia and Albuquerque, and then he quit that and went to Illinois, the same place Chandler was, to do PRISM. So PRISM, and he puts a P for polymer. So, but one unfortunate feature of this is that PRISM, Paul Flory had already published a book that he won the Nobel Prize for called, and the theory was called PRISM, Polymer Rotational Isomeric State Model, which means like you take all the rotational energies and you calculate the chain structure. That we talked about that a little bit, like the butene thing where you rotate the things and there's an energy diagram and you calculate the bonds, how the bonds can be arranged. That's called PRISM, Polymer Rotational Isomeric State Model. And this is RISM, which is whatever polymer RISM, whatever RISM was. It's not isomeric state. Like every time I see it, I want to say isomeric state, but it's not. So it's whatever RISM was from Chandler, which would have been another Nobel Prize probably if, I don't know if he'd played his cards right, but and it comes down to political, right? Like the US can only win so many Nobel Prizes, and then it'll be like they have to rotate around the world. So all the developed countries, like Nigeria won't get one, except for a peace prize or something. Right? But basically in science, it's going to be like Germany, France, England, Japan, maybe China, Korea. Yeah, literature. Well, the Kenyan one in literature recently. Yeah, Nigeria got one too. Actually, the recent one was Nigeria, right? Literature, yeah. But they won't give science, because it's a pecking order. Like they have to give to certain. Okay. Everyone's lined up. Like there's people queued up. There's a short list for Nobel Prize, and they're by country. It's it's Europe, so it's a political thing. So they can't give like De Gennes won the Nobel Prize and Edwards was British. He didn't get it because the British already had won one. So they didn't give it to both of them for whatever political. Sometimes they share a Nobel Prize, right? So like the buckyball, there were like 4 people or something, but. Anyway, so Chandler didn't get it probably for some reason like that, because it's pretty important what he did. I mean, in terms of computer simulations, it's important. So anyway, it's this paper. So they have this thing. So they're a little bit. I mean, it seems like they're disingenuous because if you look, all right. So that's their model. So if you look at the first thing I cite here, McKay, 2006. This is they're 2022, right? So McKay, 2006, and this is a paper, like maybe it's 500, 800 citations, something big, maybe more, I don't know. But so he's got this model where he says like, well, there's a white, it's kind of like the polymer. And then there's these sites where there's a different kind of interaction between the particles, and that, depending on the particle size, that orange part becomes a bigger part of the whole. Right. So if you have small particles, that orange part can be almost the whole thing, where you squeeze whatever's in between, which is polymers. Right. So they don't, I don't think they even mention that in this paper. Like this is his model. So it's the same model, it's like, so he's got this squeeze part and he says the whole game is like that squeeze part, like for how the particles organize. And then there's this background polymer, kind of relaxation time, and then there's this squeeze part thing where all the action is. And then there's a kind of a glassy region around so nanoparticles, the chains kind of stick to the surface, so they have less mobility, so they get a lower glass transition. So they can be, say, like there's a glass transition at the surface, so the particle is actually larger than what it looked like, because it's got this shell of bound polymer around it. Then there's a matrix, which is just the ordinary stuff. And then this Schweitzer thing, he's making a big deal out of that. He gets clusters, and then this is, he calls it dilatometric, meaning we talked about dilatometric stress, like if you pull on something, there's a volumetric stress on it. In other words, you're trying to change the volume and you pull on it, versus shear where you don't, right? So he says this is a dilatometric stress, or a dilatometric motion, like a time constant, like in other words, the thing breathes, like it has to pull out, and then it's due to this squeeze part that it doesn't, not able to do that. So all the dynamics of the particles moving apart is going to be focused on this little region right here. And the smaller the particles, the bigger the little region gets. So if you get nanoparticles, that becomes dominant. If they're macro particles, there's almost none of that. Right. So that's kind of the idea why you want to have nanoparticles, is that you get more of that kind of region, which it's not an original idea, you know. And so it's been around, this is 2022, so it's been around like 15 years since McKay. It probably was around before that. I mean, so anyway, so that's the theme of this thing. And they're going to use this prism equation to calculate the correlation functions in these things and get the kind of the dynamics of it. Let's see. So that's part of the thing. So these are just the questions. All right. So what's going on here? So he says he's talking about the time, the relaxation time, right? And so it's the same story. So this is basically the Arrhenius equation. So we have beta is 1 over kT. So beta is the inverse temperature. So you have delta E over kT. It's not minus, but he takes care of that because delta E is minus itself. Depends how you define delta E, if it's plus minus. So that's the Arrhenius function, right? The kind of rate law, like with temperature, why the viscosity drops when you have a higher temperature. Right? It follows an exponential decay. Right? And this comes from log of that is the energy, log of the dynamics of it. So this is like a probability. There's a probability of an event happening, has to do with the time, how often it happens. So the log of that probability is going to be related to the energy. That's Boltzmann's idea. Omega, the number of possible states that something can have. Log of that is kT times the, or log of the probability is E over kT or something, right? For Boltzmann. Negative E over kT, or S over kT. So it's assuming that it's like a random state, so there's no H, so it's just E. And so E is S, ST, whatever. So anyway, so that's just the Arrhenius function, kinetics, same as the Boltzmann function, same as the Irene rate law. They're all kind of the same thing, right? They're all an exponential. The ones, anyway, so then he says he has this tau poly, which is the blue part, or the white part for what's his name, for the other guy. The white part would be tau, poly, and then this bound layer or whatever. So there's a bound layer, and there's also this kind of tightly constrained layer. That's this delta E thing. So he's going to change. So across this thing, he's going to change what polymer he uses. So the blue polymer is going to be 2-vinyl pyridine, polymethyl methacrylate, so plexiglass, and polyvinyl acetate. So that's like acetic acid stuck to a vinyl group. This is a methyl and then acrylic side group. And this thing has a nitrogen, like it's like almost like an aromatic ring, but it's got a nitrogen on it. So that's PV2 pyrrolidone. So it's kind of like polystyrene with a nitrogen in it. It's like a polar polystyrene almost. Right, and they have different interactions with the nanoparticles. I think the nanoparticles are silica spheres. So again, it's like monodispersed silica spheres, and then they have this binding thing in it that holds them together. So he's following along the same themes and kind of looking at the dynamics of this thing. And then you can measure the dynamics of that using quasi-elastic X-ray scattering. So that's what Yevitt did, right? So Yevitt. So there, and all right. So this is before that. So 2020. So 2 years before. So Yevitt's the new faculty guy in materials, wherever he is here. Yevitt's the second guy here. And he was doing a postdoc with Koga. It's at Stony Brook, New York, Long Island, kind of near Brookhaven, where the synchrotron is. And Schweitzer's here. And then Sokolov is University of Tennessee in Oak Ridge. and then he's a theory guy. And then Yevit and Zoo, I guess is the same Zoo as this Zoo, right? This is also Zoo. So anyway, they measured this stuff. They measured this correlation function. This is a correlation function versus position that they get from scattering by doing a Fourier transform. And it's just following along the same theme. Like you get these clusters of the beads in the middle. Then they get this structure factor, right? And then they compare it actually to the Schweitzer thing. Then we compare it in the supplemental part of this thing. So the supplemental supporting info, even though this is a macromolecules paper, I think, so it doesn't need, you don't need to have a supplemental. Like you can put it into the paper, especially an important thing like actually comparing the things. So that's a comparison. The measurement is the red, and the theory prediction of Schweitzer is the red line. This is pretty good. I mean, they almost look exactly the same. They say like there's discrepancies, but I mean the important part of this is the dips. So this correlation function, this is a structure factor, but basically the dips in the energy function that they get from this are going to be where the particles are forced to be. So the atoms are kind of forced to be in these peaks. So in other words, there's the first one and the second one, and the rest of them don't matter, which gives rise to their picture here. You'll notice there's two beads in the middle. There's two bead things. So there could be one set of beads and there's two beads, and the other, when they're further apart than that, then it's gray. And I say it's just gray because he's going to get the energy function for that. And he says like the beads are going to be at the minima of this energy function. Like they're going to be at this is the well where they got to reside. And he's going to count only the first and second as this bead barrier thing. And the other ones are insignificant. So saying that's the energy that keeps the bead stuck there. And that's going to govern the time. You're going to get the time from that energy. So this WR comes from the correlation function. And CFR is the number of these bead atoms in the system. So as you change the distance, so you have the sphere, so you have to subtract off the sphere diameter. And then you have the position where you are minus the sphere diameter gives you the gap distance between these things divided by sigma, which is how big a bead is. So his polymer is made up of beads. And his nanoparticles are also beads. The nanoparticle beads are larger than the polymer beads. And then the molecular weight of the polymer gives a rate of gyration that's much larger than the particles. That means he doesn't have to worry about molecular weight of the polymer. As I've shown before, that the molecular weight of polymer is much bigger, or the size of the polymer is much bigger than the beads, then it's molecular weight independent. It plateaus out, so you don't need to worry. So they're both in the experiment and in the simulation, they're looking at polymers that are huge compared to the bead size. You can see this gets to be like one thing on top of another. Like you have to kind of consider all features of these systems, and also keep in mind that this isn't anywhere close. So keep in mind a picture of a tire, is the main nanocomposite, and it's nothing to do with monodispersed beads. So the topic that they're looking at and the problem they've framed up is so far from any reality thing. There's a disconnect. That has something to do with the demise of the field, like all the theory is just these perfect spheres, and the actual thing is this agglomerated immiscible system. So they're trying to make the spheres more miscible, but the actual system's immiscible, and it's actually not spheres, it's polydispersed things, and it's also aggregates, right? So what's the connection? Well, I mean, you're not going to get a correlation function for the real system, put it that way. Like you're not going to get this kind of thing. Anyway, but they get this. So there's a bunch of equations in here that relate one thing to another. So basically they run their little thing and it spits out this correlation function. That's their answer. Like they put in their parameters, that spring constant between the beads, the energy of interaction, like Leonard-Jones between the 612 potential between the things. And then they put it into their integral function. He lists all the parameters here that he puts in. Now, some of them you don't know what they are, but basically it spits out the correlation function. I guess that's the important part. And he doesn't explain anything about it. If you want to know this enough that you need to know it's in this Tyler paper. The first part, Tyler Martin describes what prism is, the context of it. He says like how you would use it, kind of where it can go. And this paper is he's just given like there's a software you can download that will do prism for you on your laptop, basically. So he's just kind of pitching his software on this paper. But the beginning part is a pretty good description from someone that didn't write prism of what prism is and how it could be used, which is a better place to hear it from. So there's a competing theory versus this kind of clustering thing is that the particles are uniformly distributed. He's kind of claiming that's what they're doing here, is what McKay was doing in 2006, is that there's a uniform distribution of the beads versus his nuance is that there's a clustering of the beads. And the clustering can cluster and uncluster, and that gives them a dynamic. Whereas if you have uniform, there's no dynamic of the clusters forming and unforming because of the uniform, and there's nothing changing, right? So anyway, so that's the nuance of this thing. That's the Schweitzer nuance to the thing, even though that kind of already existed. I think it's an argument that it isn't here. I think it's kind of here also. They just aren't looking at dynamics. So anyway, so if you take that idea that they're uniformly distributed, you get that this energy, so the energy of interaction, which comes back to this mother equation. So we have the energy of, so this is energy, this would be another exponential function with an energy for the polymer interaction. That would also be Arrhenius in temperature. This is the function just for those bead things. So the total relaxation time would be a convolution of those two things, right? So basically that energy of just the bead interaction, if you have a uniform field, you can just do some calculations and figure out, like you have this separation distance and how it relates to the concentration. And then you can somehow figure out that energy should go with the 1 over the square of the separation distance. And that's one of their results that they show in here. So they say, I think they show, so these lines, I think the lines, this is the energy. So KT times the energy is just the energy because KT is fixed. And then this is 1 over the square, right? And if that's a straight line, that means the uniform function works. So that kind of works. Like, in other words, they're showing that the thing that people said that there are no clusters, that it's uniform, they demonstrate that that works in their supplemental. They don't show it in the paper, but they mention in the paper that it works. But they say it's a coincidence because their function also predicts the same behavior. So there's no way to distinguish based on this energy that you get from the relaxation time, how this dependence would go. In other words, it's the same dependence. So they say this verifies their thing, but it also verifies an opposite argument. I can see this is like packed full of confusing stuff, like all of the nuances of this kind of bead dispersion thing. Anyway, so there's routes they go to get the so this is the other theory, this business of the 1/3 of the, and I think we've seen that 1/3 law in some, it's in the review papers. If you look at them, there's this 1/3 concentration law for the separation distance. It's just a volumetric argument. It wouldn't be hard to probably describe that, but I haven't done it. I mean, cube root of volume would give you a distance, put it that way. So it kind of makes sense. It would be a cube root. So the glassy bridge concept, blah, 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 blah. And then confinements, glassy layers. So then he comes down to, well, what is that delta E? So he's got this Arrhenius function and it's got an energy in it. What is that energy? Well, it's going to be like the number of these beads, like how many beads are there? That's going to be one parameter. And it's going to be like the energy of interaction is delta W of the beads. Right. So that kind of makes sense. This is kind of simple in a sense, but and then the delta W you get from prism, right? So you're going to get the delta W from, so capital W. So this is the mean field, potential mean field. PMF is what is it? The corresponding PMF. Yes. Potential of mean force. So all that is like if you plot out the energy of the beads as a function of separation distance of the beads, that's the potential of mean force. It's just the energy of the beads as they come close and far apart. So it's a complicated word for just the energy, right? So, and he keeps using PMF, and you have to try to figure out like what is he talking about, you know?
Using that for the equation.
Yeah. What?
No.
This equation.
Yeah, I mean, there's also another equation that talks about the.
Right. It's a little bit involved. Yeah. So you're going to do. So you can think about this correlation function as kind of like a probability of finding two things that are separated distance r. So log of a probability, Boltzmann tells you that's the energy. Right. So this is called the Boltzmann something model, not model, Boltzmann something or other. So in this kind of Ornstein-Zernike approach of things, this function to get the energy from the correlation function is called the Boltzmann something or other. And it's saying that the correlation function is basically saying I have a particle here. What's the probability of finding another particle? If I choose every other particle, I choose every other. So I'm taking double integral of starting particle and end particle and get this G of R, right? So it's a probability in the end. It goes from 0 to 1. Log of the probability, log of omega gives you the energy by Boltzmann. Or, right, so basically that's they call this the Boltzmann something or other. So it's going to give you, because G of R is a function of R, it's going to give you the energy as a function of R, right? And then this little W, I think is the integral of that. Let's see, from which one can determine little W. I think you get it by an integral of the potentials, blah, 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 blah. So it's an integral of G of R. Z of R is the number of the bead things, I think. So anyway, everything's like related to everything else here. NB is capital Z of R of M. So how many beads are at some distance RM, which is the first local minimum. So at the end, you plot out the energy which you get from the correlation function by taking a log, then versus this distance, separation distance minus the particle distance size. So you get just from that surface out. That thing has minima, and that's where you have to park your particles because they're going to want to be at the energy minima. So you want to know what that energy barrier is. Delta W, I guess that's what delta W is, the energy barrier of this thing. Of the plot out W versus R. The barrier, and you just define this RM is like where that first, so you have two beads. That's why he shows two beads, the first one and the second one, because the first one disappears if you go to low concentration. So the second one's still there, so you can still have an RM. So you need two, just because of the way the data worked out. And he kind of makes some argument for why you need two, but basically you need two because you need to have an RM at 0.06 and there's no first bead there. So you have to have two beads in that condition. All right, so and as you increase, you can imagine the pressure on the particles gets larger as you increase the concentration because it push cube root of the concentration is going to push them together. So basically that's why the thing shows up that way. Kind of makes sense, you know. I mean, it's really complicated, but it's also pretty simple. I don't know, so kind of a mixture of both. And also, I mean, keep in mind, it's going nowhere because this system is not anywhere close to anything real. He isn't even putting grafted chains on his beads. This is just beads. If you put grafted chains on, it would become a lot more complicated. So compare this to like carbon black in a tire that has a hierarchical structure that forms, you know, that's got at least 4 levels of structure until you get to the tear strength that you want out of your nanocomposite. So this isn't even scratching the surface of like what the actual problem is, right? Yeah, you can get money to do it. So who do they, that's what you always want to look at is like, who's paying for this? So this is like acknowledgement, Department of Energy, I guess is paying for it or something. Actually, no one paid for it because the Department of Energy is just the beam time at the synchrotron. So, I mean, it makes sense that no one's paying for it because it's kind of like, you know, going nowhere here. Anyway, maybe at Illinois they don't need money. Maybe they got their own. They have an NSF center, for. And then anyway, so we got that business. So these things all can kind of fit together. And then this he says figure 3 is our main result. So this is the meat of the 2-page paper or whatever. So what does he have? Well, as you increase the loading, the particle thing goes up. Right. So that kind of makes sense because you just expect that. And as he increases the energy, so there's nanoparticle interaction, and there's PP, Polymer interaction, and there's PN, which is Polymer nanoparticle interactions. There's 3 kinds of energy. So he keeps a P and NN constant, and then he says what the values are, and he changes this Polymer nanoparticle, and as he increases, so nanoparticles become I guess more repellent or something. Is this, if it's negative, it's attractive. If it's positive, it means they're repellent, right? So the nanoparticles become more attractive to themselves and repel the whatever. So PN gets higher. That means a worse situation for the nanoparticles. And then as you do that, you get more of these bound things.
So the arrow is indicating is it increase or
Right, increase. He says what the green, whatever are, but basically those increase in the direction of the arrow. Yeah. And so it's just like if you had that concentration or that concentration, they have the same number of these bound beads. So that kind of makes sense. Then in the inset, so he tries to make these curves all fall on top of each other in each of these things. It works in a few cases. And then this log GC total, he explains what that is. GC total is if you take the NNs and then so you divide by the NN correlation function for the first minima and for the second minima, and the potential function for the 2 beads like first and second, different R positions. And then you get the probability that they're in the first 2 things. And if you divide, what is this, log of that probability that they're in the first 2 things versus concentration, I don't remember exactly what he gets out of that. It doesn't make them fall on top, or linearizes it. It makes it linear in concentration instead of this curve thing. So it's a log of it's kind of, NB is kind of the same thing as GC total. So you take a log of NB. In other words, it's exponential in concentration. And he shows NB is exponential in concentration. So this just shows that function works. Why it's exponential in concentration, I think he doesn't say why. For given traction strength by exponential with A insensitive, blah, 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 this form is physically motivated by the predicted delta function like bridging peaks in GR, since NB equals the integral of GR prime, it follows that roughly NB go with GC total. Numerically, we find GC. So numerically we find, that means this is empirical. So that inset is just their empirical function makes it linear. They're winging it. I mean, it's basically, right, you can say it makes sense that the higher the concentration, the more of these beads, because you have more nanoparticles in the system. And if you just had exactly the same number of bonding things, you would have more just with the concentration. It would be proportional. So he puts that as a lead thing. And then this other term is exponential because he says so. That's why, because numerically we find, this means we say so. It's empirical. We could just say that's how it behaves. Then this thing, then is W, his energy barrier thing. So W is going to be wherever that plot is. But is it in here or something? Or it's the energy barrier for the first whatever. It's this energy barrier for the second particle, like how strongly are they held in. So he normalizes it by the temperature, I guess, but these are all at the same temperature, so beta is just a constant. And that decays with the loading. So you saw, I think, in these curves that the concentration goes up, that thing decays down. That barrier drops. Right. So that's the simulation result. So, and then he just shows the same thing here, just plotting those peaks versus different polymer nanoparticle interactions. So if he increases the repulsion of the nanoparticles from the polymer or increases their attraction, he gets a higher energy of holding the beads in the boundary. That makes sense. As you increase the loading, this drops. That's from his simulation. So he can make that fall off if he says, if he subtracts from delta W the polymer nanoparticle energy, then he can make all these curves fall on top of each other, which kind of makes, but there's still this weird shape, right? So that just says that this shifting is due to this EPN, which kind of is inferred when he did it. So I mean, that works to make it universal isn't like profound, like because he puts this thing in, it shifts the curves. So if I take it out, the curves go back on top of each other, right? So that's kind of nonsense again. Like this is kind of nonsense. That's kind of nonsense. So, I mean, I guess it looks good. Like whenever you can get the curves to fall on top of each other, it looks good. And it also means that it's kind of consistent, I guess, like what he put in, he got out. But that's always a good feature of doing simulations. But then 3B shows the barrier. So, so why it drops? It drops because that's the result of this simulation, I guess. Generally decreased loading reflects reduced free energy cost of local unfavorable separation of a tag pair. The data collapse, right? That's useless. So he gets this exponential dependence of the energy with concentration. Again, numerical are well fit by. So that just means, well fit by just means he's making that up, right? Like we just have this equation. So that's it. That's how it goes. And then the last one is the delta E. Delta E is the original thing. So he's going to use this stuff to get delta E so that he can calculate the relaxation time, right? That's kind of his point. He wants to get delta E. And delta E he gets from, where does delta E come from? Is delta E in this plot? No. This is W, that's delta W. Delta E is related to delta W. Compared to experimental, to get delta E, it's simple. How do you get delta E? Yeah, it's the activation energy. Let's just get that though. I'm losing it now. Delta E comes out of this thing here. Oh, delta E is NB, number of bonds times delta W. So it's just proportional to delta W times an NB, the number of those things. All right, that's it. That was equation 2. All right, so
Delta E is different from equation 2.
yeah, equation 2 gives you delta E from just that simple thing, like how many bonds in delta W. All right, I knew it was simple, but it's like, anyway, so he gets delta E as a function of loading, and then he gets these weird shapes. And then if he divides it by lambda, okay, so what is lambda? Lambda is like this PN thing again. So lambda, in order to figure out what lambda is, you have to go to the supplemental, and then he shows like a plot where he gets lambda from somewhere here. So that's beta by lambda. Somewhere he shows how that's lambda versus PN, and so versus just the energy. So lambda is a function of the energies that he put in, like the PN energies. And then, so lambda is some function of the energy PN. It's like similar to when he just subtracted off. Like he just subtracts off PN to get the things to fall. Dividing that by lambda kind of is the same thing, and it makes them all fall in the same curve. Then this matches pretty well with the experimental in the Yavet paper, like this delta E. Oh, it shows that here. The points are from the Yavet paper, the guy that's here now, and then the lines are from his simulation. In other words, the lines are the same lines as these lines, just replotted, and he just puts on the experimental on top. And he does the same compression of the experimental and In fact, this is where he gets the EPN from. Like he gets the EPN because how does he know what the EPN is for the polyvinyl pyrrolidone and the PMMA? And he gets that from taking the experimental and making this plot. And where does he get delta E from the experimental? He gets that from doing a time temperature superposition. So it's going to be like in other words, if you take the shift factor from time temperature superposition for this relaxation mode of those beads, which you can get from quasi-elastic X-ray scattering. So you find the position of the beads on an X-ray scattering pattern, I versus Q. You go to that Q, and they do the time dependence of the intensity, and that's going to be an exponential decay in time. And you fit that, and then you get tau. And then do that tau as a function of temperature, then you can get the shift factor, this AT. And the energy in the shift factor, it's exponential energy over KT is the shift factor. That's the delta E. A little bit convoluted, but basically you do this dynamic X-ray scattering measurement on the nanoparticles, do it as a function of time, just do a decay function to get this energy, and then use the energy, and that's where he gets this delta E here, he's plotting, delta E over KT, the dots, And then he uses that. He basically uses that experimental to calculate what lambda is, and then he shows that the lambda brings the experimental back onto a line. In other words, it's like circular logic. Right? He gets the lambda value of 6.8 and 3 and 5 from the experimental. He puts that into his simulation, and then his simulation matches with the experimental. It's tricky, kind of. Like he's a little bit kind of lying in a sense. I mean, it all works out, so that's nice. It means that it's consistent, like the computer spits out what you put in, which is good. But basically, first off, the whole idea of the project is kind of misguided, And then finally, a lot of it is just saying, I got out what I put in. Like when you finally, and you spend a couple hours looking at it, and you finally realize all he's saying is I got out what I put into this thing. So it's okay. It's a good example of like how a smart guy can get a paper published, or whatever, I mean, it's interesting and all, and it's got a lot of the topics in it of but basically the final outcome of this, like, what is it? Like, what do you get out of this? What are you going to get that you can use to make a better tire? I mean, I'm not sure that there's anything there really, but maybe there is, maybe there isn't. It kind of gives you an impression that you know more. A lot of it's just the feeling you have, like I learned something in this class. If you might have learned a ton of stuff in a class, you walk out and you're wandering around like, whoa, where am I, or something, and then you feel like you didn't learn anything, like thermodynamics. I mean, in undergrad thermodynamics first course, and you actually assimilated a lot of pieces, but you never actually put it together into a story. So entropy, enthalpy, a couple things, energy constant, energy sums to zero, whatever. But you don't really have any idea like how you could apply it or anything. And later on you find out. So somehow like you could do something, but this paper makes you feel like you learned something. But then when you go back and say like, well, I learned so much from that paper, and then you say like, well, what did I actually learn? And it's like, well, I learned about a system that there's no real system like that I could actually use it. It's all constructed on a computer basically. So maybe it doesn't even really exist. And then but I feel like I have a strong understanding of these bonded beads between these particles and how they change when I change the PN energy. So it's kind of like playing a computer game, and it's in the end, right? You played the game, you won, you took over the town, you saved somebody from something, and like in the end, you're still in the same place, and your car still stinks, and whatever. So it's kind of a feel-good paper in a sense like that, if you bother to read it. So, I don't know. Anyway, so I don't want to get too much down on it. And Schweitzer's a really, really kind and nice person. He's a great person to talk to and stuff. But basically, you wonder about some of this. It's kind of it's typical of like an experimental person looking at simulation and saying like, "What are you doing?" So, anyway, that's pretty much where this is going. I think I answered most of the questions in this. Probably more than that, but so So this is just saying, this is important, like to be able to say what the origin of the Arrhenius function is. And it comes back to, I think he originally said, like you have two beads, there's a bead that has to pass through and the other two beads have to move. The beads are all moving by temperature. See, there's an energy barrier for that bead to get through. And once it gets through, then it's free. So that's flow. That's the definition of fluid flow. So the viscosity is going to be proportional to that exponential, the KT, that probability of the things moving apart. Right? That's kind of the Arrhenius function. So any system that fits that picture is going to work with the Arrhenius function. Yeah, so basically this one is this one's kind of similar. I mean, it's got two beads and those beads that have to move. So it looks like maybe it would work. I mean, kind of seems like it would, might not, but it might, you know. So basically having a picture of what an Arrhenius function, what does that mean? Like what model, like the model that goes with it. And then does the thing you're looking at fit that model or not? Almost everything will fit that model, but to some extent, like what are the limitations, you know? Is it appropriate? I mean, I'd say yes, but basically you could say no if you wanted to argue it. But being able to say what is the model for Arrhenius, like that's important. Anyway, I think I answered all the other things here. If not, why don't you email me? But basically I kind of went through these things when I talked about the graphs, like the last part's the two graphs, like the inset and the graph and what are they doing in that. So hopefully that'll be okay. If email me, like no one's been emailing questions. Well, one person emailed one question, but you know. So yeah, why don't we quit there? So anyway, yeah, so Monday Satish will be here. Yeah.